word arrangement, specific positions occupied by a particular item. In this presentation, we'll learn how to arrange a word with a particular position being occupied by a particular item. Let us recall the fundamental counting principle, which simply states that if there are m ways to do one thing and n ways to do the other thing, then there are m times n ways to do both things. Also, we need to recall the rule for treating repeated letters as the same and letters used once. The rule states the number of different ways that n letters can be arranged where m1 of the letters are identical, m2 of the letters are identical, m3 of the letters are identical, and so on up to mn of the letters are identical, is given by n factorial over m1 factorial times m2 factorial, and so on up to mn factorial. But let us recall that n factorial is the arrangement of n different letters. When you look at the denominator, m1 factorial is the arrangement of m1 repeating letters. But as we arrange them, we treat them as different. This is why if we have m1 repeating letters, then arranging them is simply m1 factorial. This is what we have underneath. Now, the example that we are going to focus on is a particular position must be occupied by a particular item. Example number 1. How many ways can you arrange the letters of kitchen if it must start with a consonant and end with a vowel? In this case, of course, I'm going to show you the vowels, then the other letters are the consonants. So I is a vowel, E is a vowel. So we only have 2 vowels. Therefore, we are saying there are 7 letters in this word, 7 places to fill with the 5 consonants and 2 vowels, right? So the fact that we want the words that we are going to form to start with a consonant and end with a vowel. Therefore, we are focusing on our attention on first position and last position. Therefore, first position, we have 5 choices. Last position, we have 2 choices. Therefore, now if you are then trying to position or to come up with the formation of the words, you need to position first the first position and the last position because there are conditions there, right? So the first position, we have 5 choices, right? Then the last position, we have 2 choices. But once the first and last position are filled, to fill position number 2, we need to subtract the 2 letters that have been positioned already. So 2 letters from 7, we now have 5 choices to make on position number 2. When you go to position number 3, will be after filling position number 2, we will be left with the 4, and so on and so forth. And at the end, this is the situation that we end up having 5 choices, first position, 2 choices, the last. These are the things that you fill first. Then when this is filled and this one is filled, you subtract from 7, we are left with the 5 to choose for the second position. Then once it's filled, we are left with the 4. Once filled, 3, and so on up to 1, right? But what allowed us to multiply the different choices is we are applying the fundamental counting principle, so that at the end, we can arrange the letters of the word kitchen, making sure that each starts with a consonant and ends with a vowel. And we can do that in 1,200 ways. I could have done that using a table. My positions 1 up to 7, because we have 7 places to fill 7 letters. The choices. So once you do it again in a table, you have to attend first to the fix the positions or the conditions that are given to say the first position, you should have a consonant. The last one, a vowel. So I first fill this position, which I have 5 choices. The last one, 2 choices. Then once I'm done, I'm saying last position first, they are filled. Then how many letters left? 5. Then second position, I have 5. Once this is filled, I have 4, and so on up to 1. Then when this is done, that is, these are the different choices to different positions. Together, we then multiply the 5 times 5 up to 2, like I have shown here. And we are allowed to do that because of the fundamental counting principle. Right, as my second example, I'm saying how many ways can you arrange the letters of the word Sibusiso if it begins with exactly 2 S's, right? Roman figure 1, treat repeated letters as different. That's the condition. As we arrange the letters of this word, wanting each word formed to start with exactly 2 S's. I have to treat repeated letters as different. Then secondly, I have to treat repeated letters as the same. Now, first and foremost, we need to make sure that you should understand what is the meaning of exactly 2 S's. Exactly 2 S's means the first 2 letters must be S's, but the third one must not be an S because of the word exactly, right? When it's written 2 S's, then it means the first 2 letters must be S's, but the third one may be an S or something else. So not the different things that are written here exactly, and there's only 2. And these 2 are very, very different. Okay, let us now attend to Roman figure 1, treating repeated letters as different arrangements, beginning with exactly 2 S's, right? Sibusiso has repeated letters S and I, but the fact that we are told that we have to treat them as different, it's like in the word Sibusiso, there is no repeating letters. They are all different. That is, if I count Sibusiso with 8 letters, so we have 8 different letters. That is the meaning of treating the repeated letters as different. Also, we note that we have 3 S's because we want to comply with the condition that the arrangements must begin with exactly 2 S's. So we have 3 of the S's, right? Since there are 3 S's here, we have 3 choices for the first position, 2 choices for the second position. That is, this is my first position. And any of the 3 S's can occupy that position. That is what it means. Once it's filled, I'm left with the 2 S's. Then in second position, any of the 2 can fill the position, right? That is what it means. Now I have filled position 1 and 2, right? Then I subtract the letters that I filled here from 8. That means now we are left with 6 letters to distribute to the remaining 6 spaces. But the third position cannot be an S. That means as I contemplate to check on how many choices do I have on third position, I have to make sure that that position we cannot place an S. So that being the case, with 6 letters that were left after filling 1 and 2, and in the 6 letters we have an S, and we don't want that S, we remove it. So in position number 3, we have only 5 choices, right? So this is what it means. So position 1 up to 3 are filled. How many letters are left? We have 5. That is 8 minus 3. So we are saying now left with the 5 letters to distribute to the remaining 5 spaces. So there are 5 choices, right, for the 4th position, and so on and so forth. That means in this position, I now have 5 choices, because the 3 have been put there. 5. Here are the choices. Then once this is filled, I remain with the 4. Filled 3, filled 2, filled 1. Right? So now I have filled all the 8 positions. Now then, these positions are different and they have different choices. So together would mean I'll multiply 3 times 2 times 5 times 5 times 4 times 3 times 2 times 1. This is what I have. And what allows me to do that is the fundamental counting principle, right? And this gives me 3,600 ways, right? But we need to know that these 3,600 ways, we obtained them treating the letters that are repeating as different. And besides that, we also responded to the condition that each word starts with exactly 2 S's. Right, we are going to use this understanding to the next coming problem. Now, we need at this point to remember that this other 3,600 is correct only if it is specified in the question that you must treat repeated letters as different. So you can see that in our case, it's correct because we are told that treat the repeated letters as different. If it was not saying, this was not going to be the answer, and this was not going to be the approach, right? Now, Roman figure 2, we should treat repeated letters as the same. Now we have the repeated letters, 3 S's and 2 I's that are in the word. When we treat them the same, that means we have to recognize that they are repeating letters that treated the same, right? So the rule n factorial over m1 factorial times m2 factorial and so on up to mn factorial is useful, but in the following manner. You need to understand that the n factorial in the rule represents arrangements of a word with any letters that are different in any positions. That means this n, we are arranging any different letters in any position. Then it's simply n factorial, right? Now, the value of that is, I'm simply saying value to mean the number that is going to occupy this, if I am to use the rule, in 1. That is, if I look at 1, because we are treating the letters as different, that means the n factorial in 1, the value of n factorial, the number that will occupy here in 1, corresponds to arranging 8 different letters in 8 positions, with each word beginning with exactly 2 S's. That is the understanding, because now we have an extra condition, so that we can not simply take the 8 different letters and say 8 factorial. No, we have to satisfy this. This is why I'm saying the value that will represent n factorial in the formula corresponds to arranging 8 different letters in 8 positions, with each word beginning with exactly 2 S's. If we understand this, then the value of that same n factorial in 2 is the same as that in 1. Because why? You know, if you are going to apply this formula, since we are now saying treating repeated letters as the same, we are supposed to apply this formula, but the way we find the numerator is not as direct as simply counting how many letters are there in the word, then we say the number of letters factorial. No, we are simply going to make sure that we respond to the exactly 2 S's, which is what we did in 1. We were treating the letters of the word sibusiso that we are repeating as different, right? And at the same time, responding to the fact that exactly 2 S's are supposed to be in each word. Therefore, the answer we got in 1 represents this n factorial, the numerator, right? So, as I have said, that the value of n factorial in 2 is the same as that in 1, but we need to consider repeated letters as the same. Meaning, we need to divide the result in 1, that is the 3,600 we got, by 3 factorial times 2 factorial. The 3 factorial representing the 3 S's we have, and the 2 factorial representing the 2 E's we have, resulting in 3,600 over 3 factorial times 2 factorial, which gives 300 ways. But otherwise, the trick is in understanding to say, for you to use this formula, the n factorial in a normal situation refers to the number of different letters in the word, then simply n factorial. But in our case, we treated the letters as different, but we are given a condition that the words that we are going to form are supposed to have exactly 2 S's. So this is why I'm saying, in a way, by trying to bring in this formula, I'm trying to understand that you realize that how are we going now, if we are going to treat the letters as different, how are we going to approach it? We need to find the corresponding value of the numerator given the condition that the word starts for exactly 2S, right? So as such, this is how I thought I should explain so that you understand. It could be you have a different explanation, But that's my explanation in trying to justify why am I taking 3,600 as the numerator when I'm applying this formula. It's because the problem itself, you have to think in such a way, because at the end of the day, the condition that is making things a bit complicated is wherein each word has to start with exactly 2 S's. I think I've tried. You can always add if ever things are not the way you think they should be.